Now we have an equation for simple harmonic motion. We can use that to solve for a given physical situation when we have actual parameters to use. So we're going to see how that works. And there are parameters for the spring constant and the mass that straight away give us the frequency, or the angular frequency in radians per second, of the motion, because omega, the angular frequency, is equal to the square root of k divided by m. The other thing we need are the initial conditions, the initial velocity and the initial position, and these determine the amplitude and phase of the motion. So let's see how that works. We'll start with a solution of this form, where we have the constant b is going to be determined by the initial conditions. The real and imaginary parts of b will be determined by the initial conditions. And the frequency omega, as I've already described, is just the root of k on m. So let's substitute in the initial position, x at time equal to 0. If we put time equal to 0 in our solution here, then we just get b plus b star. So the initial position 2 must be equal to b plus b star. So 2 times the real part of b, because it's the sum of b with its complex conjugate, 2 times the real part of b must be equal to 1. So now we have the real part of b all nice and solved. What about the imaginary part of b? Well, we can get that from the velocity. We take the derivative of x and put in time equal to 0. And at time equal to 0, we have the condition that the velocity is -1, and that must be equal to b times I omega minus b star times I omega. Take out a factor of I omega, and because we have an I here multiplying the difference in the complex conjugate and itself, we get that -2 times omega must be equal to the imaginary part of b, which means the imaginary part of b must be equal to 2 divided by omega. So now we have the real and imaginary parts of b. We know what omega is. So we have that b is equal to 1 plus I divided by 2 root 5. And that gives us, substituting in b and its complex conjugate, this gives us an equation for x. Now we know this is a real valued thing because we have something here plus its complex conjugate, so we can expand the complex exponentials and get this in terms of sine and cosine functions. And it looks like this. 2 times root 5 times t minus 1 on root 5 sine root 5t. So root 5 here is the frequency omega. And what we see actually is really something kind of cool. And that is the initial position here is the factor outside the cosine function. And the initial velocity is here, this -1, divided by the frequency. So the factor in front of the cosine function is the initial position. The factor in front of the sine function is the initial velocity divided by the frequency omega. And we can also use some trigonometric relationships here to condense this sine and cosine function into a single trigonometric function, which is a cosine with the same frequency, but now some phase offset here. So that's what the solution looks like if we use this form of x of t. What about if we use this form here, a of e to the I omega t? Well, kind of works the same way, right? So, but the solution looks a little different. So we substitute in the initial position, which gives us the real part of this function a e to the I phi must be equal to 2, which means a cosine phi is equal to 2. Similar sort of thing with the initial velocity. We get that a sine phi must be equal to 1 on omega. We already know the value of omega, and by summing the square of these two, we can get that a squared is equal to 21 on 5. We can get the phase by doing dividing these two by each other, and what we end up here then is the same solution.